Hello guys, so today we're going to be revising for the chemistry periodic that's coming up. So grid question number 1 from chapter 13 says, the following quantities of gas were found to be present in a 2 decimeter cubed vessel at equilibrium. So we have 4 moles of O2, 10 moles of SO2, and 20 moles of SO3. Part A asks us to write the equilibrium law for the following reaction. So I'll give you guys a bit to do it. Okay, we need to put the partial pressure, or in this case the concentration of the gaseous or aqueous products over the gaseous or aqueous reactants. So then K is equal to the concentration of SO squared, because its coefficient has a 2, over concentration of O2 times concentration of SO2 squared, because the coefficient is a 2. Part B and C ask for the same thing, which is the value of K in the following 2 reactions. So I'll give you guys a bit to solve. Okay, so what we need to do first is find the value of K for the original reaction. What we need to do first is find the concentration of each reacting species. So as we know, the formula to find the concentration is C is equal to N over V. So we just have to divide the number of moles by the volume to find the concentration. So for O2, it's 2 molar. For SO2, it's 5 molar. And for SO3, it's 10 molar. Now the K, as we said, is equal to SO3, concentration of SO3 squared, so 10 squared, over concentration of oxygen times the concentration of SO2 squared, so 5 squared. And we get that to be 2. Now for this reaction, we see that the coefficients were all halved, so the value of K prime is equal to the value of K to the power of half, which is equal to the root of 2, or simply 1.4. In the bottom reaction, you see that the coefficients were all doubled. The value of K prime prime is equal to the value of K squared, which is equal to 4. So this question says a sample containing 2 moles of H2, 2 moles of I2, and 10 moles of HI were introduced into a 2 decimeter cube vessel at a temperature where the following reaction occurred. So as we said, to find the reaction quotient, we need to put the concentration of the products to the power of their coefficient over the concentration of the reactants to the power of their coefficient. And the concentration of HI is 5, concentration of H2 is 1, and the concentration of I2 is 1. So we find this to be 25, which is not equal to 10, meaning that we'll have to find the concentration of all species at equilibrium. So what we have to do is to draw the ice table with this reaction proceeding. Now we got Q to be 25, which is greater than 10. If we think of it mathematically, the concentration of HI is too high and the concentration of H2 and I2 is too low. So we can just conclude that the backward reaction is what proceeds. So we start off with 1 molar of H2, 1 molar of I2, and 5 molar of HI. Remember the concentrations? So we have 1, 1, and 5. Now, as we said, the backward reaction is proceeding. So H2 and I2 both get plus x, and HI gets minus 2x because the coefficient is 2. So at equilibrium, H2 would be 1 plus x, I2 would be 1 plus x, and HI would be 5 minus 2x. 10 is equal to 5 minus 2x, remember squared, because the coefficient is 2, over 1 plus x times 1 plus x, or simply 1 plus x squared. Now we can just find the root of the entire equation. So that we get root 10 is equal to 5 minus 2x over 1 plus x, and then we can just solve for x. We get x to be 0.357 molar, but that's not the final answer. So we know that the concentration of HI is equal to 2x, which is equal to 4.29 molar, while the concentration of H2 is equal to the concentration of I2, which is equal to 1.36 molar. Now this question says that a sample containing 4 moles of each H2 and CO2 were introduced into a 4 decimeter cubed vessel where the following reaction proceeded and has an equilibrium constant of 4. Now they want us to calculate the equilibrium concentration of all gases. So I'll give you guys a bit to solve. Okay, so what we need to do here is the ice table. So we have this reaction proceeding, and we started off with 0 molar of carbon monoxide, 0 molar of H2O, 4 moles in a 4 decimeter cubed, so 1 molar of H2 and 1 molar of CO2. Now, because these two were introduced, the backward reaction is what proceeds. So we have plus x minus x minus x. So we end up with x, 1 minus x, and 1 minus x. We have to write the reaction quotient. So we know that the equilibrium constant K is equal to 4, which is also equal to 1 minus x squared over x squared. Now, if we do the root of all of this, we get 2 is equal to 1 minus x over x. We just substitute, so 2x is equal to 1 minus x. So x is equal to 0.33 of H2, which is equal to CO2 to be equal to 1 minus x. So that's equal to 0.67. And we found the concentration of CO and H2O to be x, which is just 0.33. Now for question number 2, we are given that the Kp of this reaction is equal to 1 times 10 to the power of minus 2. And they just want us to find the partial pressures of NH3 and HCl. So I'll give you guys a bit to solve. Okay, so the Kp is equal to the partial pressure of NH3 times the partial pressure of HCl. Now we don't include NH4Cl because in this case it's a solid, and even if it was a liquid, because in this case it's a solid. So simply find that the partial pressure of NH3 is equal to the partial pressure of HCl, which is equal to the root of 1 times 10 to the power of minus 2, or just simply 0.1. I'll give you guys a bit to solve question number 3. Okay, so part A asks us to find the partial pressure of carbon monoxide. To find the partial pressure of carbon monoxide, we need to find the total pressure and subtract that by the partial pressure of carbon dioxide. Now we are given that the partial pressure of carbon dioxide is 0.82 atmospheres, but to determine the total pressure of all gases, we need to look at this table. Now, if we look at here, we see that at the time between 4 hours and 5 hours, the total pressure stops changing. So we can conclude that this is going to be the final pressure. We get the partial pressure of carbon monoxide to be 3.38. In part II, they ask us to find the value of Kp. So we have 2 CO, so it's the partial pressure of CO, but squared because the coefficient is 2, over the partial pressure of CO2. Now we don't include carbon because it's a solid. 38 squared over 0.82 is equal to 14. Part B asks if a suitable solid catalyst was placed in the reaction vessel, would the final total pressure of the gases be greater than, less than, or equal to the final total pressure of the gases without the catalyst? So we can just look at it from the perspective that it's a catalyst, and the catalyst has no actual effect on the reaction. It just provides a path of lower activation energy. So we can justify that the final total pressure of gases at equilibrium will just be equal to the final total pressure of gases at equilibrium without the catalyst. I'll give you guys a bit to think about question number 4. Even though doubling the volume will have the pressure of both of them, it will have no effect on the equilibrium because N-butane and isobutane react with the same ratios. We can just consider the doubling of the volume to be halving of the concentration because, as we know, C is equal to N over V. When the volume is doubled, the concentration is halved. We can then just say that the concentration will be 2.5 times 10 to the power of minus 5 molar. I'll give you guys a bit to solve question number 5. Okay, so part A wants us to find the initial concentration of AS5 in the container. Concentration is equal number of moles divided by volume. Now we can find the number of moles by dividing the mass over the molar mass of AS5, and the volume is 10.5 liters, which is 10.5 decimeter cubed. If we first calculate the number of moles, we get 0.164, and then all we need to do is divide that by the volume. Concentration to be equal to 0.0156 molar. Now in part B, they want us to find the equilibrium constant for the decomposition of AsF5. F2 times ASF3 over ASF5. So part C says that 30% of the original number of moles of AS5 decomposed, and they want us to calculate the molar concentration at equilibrium and the value of the equilibrium constant. So if 30% decomposed, that means that we are left with 70% of the original number of moles of AS5. So to find the molar concentration of AS5, we just do 70% or 0.7 times the answer we got, which was 0.0156, and we get it to be equal to 0.0109 molar. Double I asks us to find the value of the equilibrium constant, K equilibrium, for the reaction. So we have 0.0156, 0 and 0, plus x, and minus x, because the reaction is proceeding forward. So we have 0.0156 minus x, and x. Now we found the molar concentration of AS5 to be 0.0109, which is equal to 0.0156 minus x. So from this, we can calculate the value of x, which is 4.7 times 10 to the power of minus 3. Now, K equilibrium is equal to the concentration of F2 times the concentration of ASF3 over the concentration of ASF5, equal to 4.7 times 10 to the power of minus 3 squared over 0.0109. And if we calculate it, we get it to be equal to 2.02 times 10 to the power of minus 3. Now part D asks us to find the mole fraction of F2 in the container at equilibrium. All we have to do is find the number of moles of F2 over the total number of moles, and we can get it. Now, to find the number of moles, we just have to multiply the concentrations we got at the end by the volume of the container. And if we calculate this, we get it to be equal to 0.0491 over 0.2126, 0.231. Question 6 gives us a graph and says that after a 2 mole sample of HBr is placed into evacuated 1 liter container at 700 Kelvin, the reaction above occurs. So I'll give you guys a bit to read the questions and solve. So part A asks to find the expression for the equilibrium constant Kc for the reaction. So as we said, Kc is equal to the concentration of gaseous or aqueous product to the power of their coefficients. So H2 to the power of 1 times Br2 to the power of 1 over the concentration of the reactants to the power of their coefficients. So over HBr squared because the coefficient is 2. Now they want us to find what HBr is at equilibrium. We can see that when the graph flattens out at this point, the concentration remains the same. We can then determine that this is when the reaction reached equilibrium. So we can see at this point that it's at 1.60 molar. So we can just say that it's 1.60 molar at equilibrium. Now, if we think of the ice table, specifically the C part, HBr would have it minus 2x, while H2 and Br2 would have a plus x each. That's because they form at half the rate that HBr decomposes. So the graph would be something like this for H2 and HBr, and they would be produced at half the rate that HBr is consumed. Now 0.4 molar of HBr was consumed, so half of that is 0.20 molar for the concentration of H2 and Br2. Part D, I just drew the graph. The rate of production of H2 is half of the rate of decomposition of HBr. Because it's being produced, the graph is going up. But we make sure that when it reaches equilibrium, the concentration remains constant. Now part E asks us to find Kc and Kp when the reaction reaches equilibrium. Kc is equal to the concentration of H2 times the concentration of Br2 over the concentration of HBr squared, because the coefficient of HBr is 2. So if we simplify that, we get 0.016. Now they want us to find Kp, and Kp is equal to Kc times RT to the power of the change in number of moles. Finding C out, we got it to be minus 2x for HBr and plus x for H2 and plus x for Br2. If we add all of these up, we get it to be 0. So the change in number of moles is 0. Kp will be equal to Kc, which will be equal to 0.016. Give you guys a bit to solve this question. In this question, they want us to find the equilibrium concentration of all gases. So what we have to do is draw the ice table. Now, they mentioned that 6 moles of H2 and I2 were introduced to a 3 decimeter cubed vessel. That means that the concentration of each is 6 divided by 3, which is equal to 2 molar. So we have 2 for H2, 2 for I2, and 0 for HI. And the forward reaction is proceeding, so we have plus 2x and minus x and minus x. So it's 2 minus x, 2 minus x, and 2x. K is equal to 25, which is equal to the concentration of HI squared, because the coefficient is 2, over concentration of H2 over times concentration of I2. Now, if we do the root of all of this, we find x to be equal 1.43 molar. So the concentration of H2 is equal to the concentration of I2, which is equal to 2 minus x, which is equal to 0.57. And then the concentration of HI is equal to 2x, which is equal to 2.86 molar. I'll give you guys a bit to solve question number 2. So we are given that NO has an initial concentration of 16 atmospheres and Cl2 has an initial concentration of 12 atmospheres with the reaction proceeding. They want us to find the value of Kp. So at first we need to do the ice table. We have 16, 12, and 0 minus 2x because of the coefficient minus x plus 2x. So it becomes 16 minus 2x, 12 minus x, and 2x. Now they mention that the total pressure at equilibrium is 24 atmospheres. That means that all of this should add up to 24. 16 minus 2x plus 12 minus x plus 2x is equal to 24, which means that x is equal to 4 atmospheres. Now Kp is equal to the partial pressure of NOCl squared over the partial pressure of NO squared times the partial pressure of Cl2, which is equal to 2x squared over 16 minus 2x times 12 minus x squared. We then find Kp to be equal to 8 squared over 8 squared times 8, which is then equal to 1 over 8 or 0.125. So I'll give you guys a minute to solve question number 3. Okay, so in question number 3, they want us to find Kp. We are given that the initial pressures of NO and Cl2 are 10 atmospheres and 6 atmospheres. So what we have to do is construct an ice table. So for NO, we start with 10, and for Cl, we start with 6, and with NOCl, we start with 0. So then it's minus 2x because of the coefficient. 6 minus x for Cl, and plus 2x for NOCl. So we end up with 10 minus 2x, 6 minus x, and 2x. We are given that the partial pressure of Cl2 at equilibrium was 2 atmospheres. It means that 6 minus x, which is the partial pressure at equilibrium, is equal to 2, meaning that x is equal to 4. A pressure is equal to the partial pressure of NOCl squared over the partial pressure of NO squared times the partial pressure of Cl2. Get that to be 8 squared over 2 squared times 2, which is equal to 8. Question 1 says that some SO2 and O2 and SO3 gases exist at equilibrium in a closed container. They want us to predict the effect of the following changes on the quantity of SO3. So I'll give you guys a minute to think about it. Okay, so because delta H is less than 0, the forward reaction is exothermic and the backward is endothermic. So let me just write that down. Every time you increase the temperature, the reaction favors the endothermic side. That means that the backward reaction will proceed, meaning that the quantity of SO3 will decrease. What about reducing the volume of the container? Well, to understand, when reducing the volume, the pressure increases. And when the pressure increases, it always favors the side with the least number of moles of gaseous species. So here we have 1 mole of SO2 and half a mole of O2, so 1.5, whereas here we have 1 mole of SO3. 1 is the less, and because pressure is increasing, it favors the side with the lower number of moles, of gaseous moles. So reducing the volume will increase the amount of SO3. Adding a catalyst does not change the reaction itself. It has no effect on the reaction except by providing a path of lower activation energy. Catalyst won't affect the amount of SO3. So question 2 part A says, what is the effect of adding NaOH to an equilibrium system containing saturated CuOH2 solution? So we have the reaction CuOH2 partially disassociates to give Cu2 plus and OH minus. Now adding NaOH or OH minus will favor the backward reaction. But because this is a solid, it has no effect, meaning that adding NaOH will increase the amount of OH because you are adding NaOH or OH minus, but it will decrease the Cu2 plus because the reaction shifts to the back. The reaction favors the left side. They then ask what is the effect on the percent yield of raising the pressure on the following equilibrium system. So increasing the pressure, as I said, favors the side with the lower number of gaseous moles. Here we have 3 plus 1, so 4. Here we have 2, so increasing the pressure favors the forward reactions, so the concentration of NH3 increases while the concentrations of N2 and H2 decrease. The temperature favors the endothermic side of the reaction. But here we know that the forward reaction is exothermic, so it favors the backward reaction in this case. So 3H2 and N2 increase while NH3 decreases.
Okay, so for section 13.7, basic question 3, you have 3 reactions. 1 is X solid with H2O gas will give you XO also gas with H2. Then the delta H is plus 131. For reaction 2, you have XO2 with H2. It will give you XO with H2O. Delta H for this one is plus 41. For number 3, you have XO, you have 2 XO, will give you X and XO2. Part A, they want you to find the Kp. So if you go back, you have this gas, this it's the product over the reactant, and you only take the gaseous molecules, so it will be H2, the partial pressure of H2 multiplied by the partial pressure of XO over the partial pressure of H2O. That's part A. For part B, they're saying for reaction 1, which is this one, if temperature increases, will the constant Kp increase, decrease, or remain the same? Temperature always favors the endothermic. The constant will always increase. I mean, the temperature always favors an endothermic reaction. If then the constant increases, if it's exothermic, it decreases. This reaction is endothermic, so it will increase. Now for part C, they want to calculate the delta H for reaction 3, and to get reaction 3 they added up the first two and reversed it. So adding them up, H2O cancels, H2 also cancels, you will get 2XO, X and XO2. So for in this state you add up the delta H's, you get 172. And then they also reversed it, so you put the minus signs. So for part C, delta H is minus 172. Now for the final one, part D, as we know, to get they want the Kp triple prime of reaction 3 in terms of Kp prime and Kp double prime. This one is for reaction 1 and this one is for reaction 2. As we know, they added up the equations first, and when they add up, the Kp's multiply. So at first it's Kp prime times Kp double prime, but and then they also reversed the reaction, so it will be the reciprocal. So this is Kp triple prime.
Nature of acids and bases. Identify conjugate acid-base pair. NH3 plus H2O makes NH4 plus into OH minus. So NH3, it accepts a proton, therefore it's a base. So when the complex of when it does accept the proton is the opposite. So this is a base, this becomes a conjugate acid. Now here, H2O into OH minus. So what it did is, it lost an electron, therefore it was lost a proton, therefore it was an acid. So the complex that is formed is therefore the opposite, which is a conjugate base. Next one, HC3H5O3, it lost a proton, so it's an acid. It donated a proton, therefore the conjugate is a base. This is a conjugate base. H2O, it gained a proton, therefore it's a proton acceptor, therefore it's a base. So H3O plus is therefore an acid, or a conjugate acid. CH3 NH3 plus, it donated a proton donor, it's an acid, so this will be the conjugate base. And H2O, it gained the proton, therefore this was a base, so this H3O plus is a conjugate acid. 14.2, explain why water becomes a better electrolyte at higher temperatures, or it's supposed to say temperatures. Simply, at higher temperatures you have more energy to break the water molecules into ions. So when you have ions, it can conduct electricity. So that's why you have it's a better electrolyte. calculate the H plus of water at temperature. Well, water, so we're assuming it's neutral, and then H2O, liquid, dissociates into H plus and OH minus. And since this is liquid and these two are aqueous, Kw is equal to concentration of H plus into concentration of OH minus. So, since they're neutral, they're the same, so all you have to do is just do square root of that, which is 2 times 10 power minus 7. Calculate the H plus and OH minus. This dissociates completely because it's a strong acid, so H plus is 0.20 molar. But OH minus, you have to use this, not this one, 10 power minus 14, because that's probably at a higher temperature. So 10 power minus 14, because you have to assume it's at 25 degrees Celsius, over 0.2. So that would be times 5, so 5 times 10 power minus 14. Now, section 14.4. Calculating pH of strong acid solutions, find the H plus and OH minus. So pH equals 3, so all you do for H plus is 10 power minus 3. And OH minus is 10 power minus 14 over that, which is equal to 10 power minus 11. POH equals 10, so OH concentration is equal to 10 power minus 10. So H plus will be 10 power minus 14 over that, which is equal to 10 power minus 4. And that's it for section 14.4.
So for section 14.5, basic question number 1, they gave you concentration of HCl to be 2.0 molar. They also gave you concentration of HF to be 1.0 molar. And the Ka of HF is 7 times 10 to the power of minus 4. They want you to find the pH. Whenever you have a weak acid and a strong acid in a solution, you ignore the weak acid and you focus on the strong acid, and since it dissociates completely, the concentration of H plus will be the same as that of the strong acid, which is, in this case, it's 2.0 molar. So pH equals minus log of the concentration of H plus, which is 2.0, which is minus 0.3. Question 2. You have percent dissociation, which is alpha of HCN. It's 5 times 10 to the minus 3%. You also have the concentration, which is 1.0 molar, and they want you to find the dissociation constant, which is Ka. The formula is Ka is equal to alpha squared C over 1 minus alpha, which is 5 times 10 to the minus 3 times 1.0 over 1 minus, this is squared, 1 minus 5 times 10 to the minus 3, which you will get, you're supposed to get 2.5 times 10 to the minus 5. Now for question number 3, the given in the answer key and the question sheet is different, so I'll just go with the given in the question sheet. They gave you the concentration of NH3 to be 2.0 molar, and they gave you Kb is 1.8 times 10 to the minus 5. They wanted to find the percent dissociation, which is alpha. First of all, we use ice table to find the concentration of OH minus, so it's H2O plus NH3 will give you NH4 plus OH minus. The given for the concentration, the initial concentration of NH3 is 2 minus X plus X plus X and then X and 2 minus X, and then Kb is X squared over 2 minus X. Kb given to be 1.8 times 10 to the minus 5 is equal to X squared over 2 minus x. You will get x to be 6 times 10 to the minus 3. And as we know from here, that's the concentration of OH minus. And then the formula for the percent dissociation, alpha, it's the concentration of OH minus over the total concentration of NH3, I mean, times 100 for the percent, which you'll get 6 times 10 to the minus 3 over 2 times 100, which is 0.29%. Now for the grid question, grid number 1 of 14.5, you have HNO2 to be a weak acid with a Ka of 5 times 10 to the minus 5 molar. I mean, not molar. They wanted to, first of all, for part A, they want to find the concentration of all species present. So you do a ice table. HNO2 will give you H plus and NO2 minus. They give you the concentration of HNO2 to be 2. This is plus x minus x, 2 minus x, x and x. And then you got the formula is I forgot to say they also, never mind, the Ka equals x squared over 2 minus x. You have Ka to be 5 times 10 to the minus 5. You have x squared, you'll get x squared, and here we make an assumption that x is very small beside the 2, so it's just x squared over 2. And then you will get for x the concentration of H plus to be 0.01. The concentration of the NO2 minus is also 0.01, and the concentration of the HNO2 it is 1.99. And as we see from the answer, our assumption was correct. Now for part B, they wanted to find the pH. As we know from part A, the concentration of H plus, it is 0.01. So I can just do pH minus log concentration of H plus, which is minus log concentration of 0.01, from which you will get 2.0. And then now for part C, the percent dissociation of HNO2, which is 2.0 molar. They want you to find alpha. So Ka equals alpha squared over alpha squared C over 1 minus alpha. Again, we do a assumption alpha is very small beside the 1. So you have the Ka given 5 times 10 to the minus 5 do you want to find alpha? You have the concentration, it's 2. You will get 5 times 10 to the minus 3. Alpha is 5 times 10 to the minus 3. And then because it's this because this percent, you multiply it by 100. You will get it to be 0.5%. So now for section 14.6, basic question number 1. You have the concentration of NaOH to be 0.2 molar. They wanted to find the pH, pOH, the concentration of H plus and the concentration of OH minus. So first of all, since it's a strong base, the concentration of OH minus is equal to the concentration of the acid, which is 0.2 molar. And then you do pOH is minus log of 0.2, which is 0.7. You can also, from here, you can get the pH, which is 14 minus 0.7, which is 13.3. And then you can get the concentration of H plus, 13.3 is minus log the concentration of H plus. You will get H plus to be 5 times 10 to the minus 14. Now for the grid questions. Grid question number 1. You have the pH equal to 12. You also have the concentration of NH3 to be 5, and they want you to find the dissociation constant Kb. So first you do the ice table to know the expression for Kb. NH3 with H2O gives you NH4 plus and OH minus. 5 minus X plus X plus X, XX, and 5 minus X. So you can see from here the expression for Kb is X squared over 5 minus X. X being the concentration of OH minus. So since you have the pH, you can get the pOH, which is 14, minus the pH, which they gave you in the question is 12, which is 2. So the concentration of OH minus, you can get it to equals minus log concentration of OH minus. You'll get the concentration of OH minus to be 0.01. Since we already know the expression, Kb is 0.01 squared over, it was 5 minus 0.01, and you will get Kb to be 2 times 10 to the minus 5. Now for question 2 of the grid, you have the pH. No, you need to find the pH. You have the concentration of NH3 to be 2.0 molar. You're also given the Kb. So the expression is NH3 with OH minus with H2O will give NH4 plus and OH minus. So since it gives OH minus, the concentration for it is Kb times the concentration of the NH3, which is radical Kb times U, which is radical 1.8 times 10 to the power of minus 5 multiplied by 2, which is which is 6 times 10 to the minus 3. Now you can get the POH. .22. pH will be 14. Minus 2.22, which is 11.78. Now for question number 3 of the grid, they want you to find the percentage association. They also gave you concentration of NH3, which is 2.0 molar, and they gave you the Kb. Now first we need to find alpha, so the formula is alpha squared c over 1 minus alpha. To find alpha, it is OH minus, which is radical KAC over the total concentration. So first if we do radical KAC, which is 1.8 times 10 to the minus 5 multiplied by the concentration, which is 2, you'll get the concentration of OH minus to be 6 times 10 to the minus 3. And then you do that over the total concentration, which is 2. You will get 3 times 10 to the minus 3. Then you actually don't need to do the expression, you just need to multiply alpha times 100, which is this times 100, which is 0.3%. 14.7 and 14.8, they're all similar. 14.7, question 1, they give you concentration of H2SO4 to be 0.2 molar. They also gave you the Ka of H2SO4 to be 1.2 times 10 to the minus 2. They want you to find the pH. So the pH is the concentration of H plus is radical KAC, which is radical 1.2 times 10 to the minus 2 multiplied by 0.2. The concentration of H plus is 0.05. So you just do pH is minus log concentration of H plus, which is 0.05, which will get you 1.3 is the pH. 14.8 now basic question 1, they want the pH of NaCN, of which the concentration is 0.2 molar, and they gave you the Ka to be 6 times 10 to the minus 10. So the concentration of H plus is radical KAC, which is radical 6 times 10 to the minus 10 multiplied by 0.2, which is 1.1 times 10 to the minus 5, and then you do pH minus log concentration of H plus, which is minus log of 1.1 times 10 to the minus 5, which is 4.96. And then now the second question, you have concentration of NH4Cl 0.1 molar, and you have the Kb equals 1.8 times 10 to the minus 5. They want you to find the pH. So in this case, the concentration of OH minus, since it's a base, is radical Kb times C, which is radical 1.8 times 10 to the minus 5 by 0.1, which is 1.34 times 10 to the minus 3. And then you'll get the P of OH to be minus log 1.34 10 to the minus 3, which is 2.87. And then the pH is 14 minus the pOH, which is 2.87, and you'll get the pH to be 11.127.
Number 3. Which of the two acids is weaker, HOI or HOBr? Justify your answer in terms of Ka. So what Ka is how much of the acid or molecules in the solution it dissociates. So higher Ka means higher dissociation, which means a stronger. So 10 power minus 11, 10 power minus 9. 10 power minus 9 is greater than 10 power minus 11, so HOBr is a stronger acid, so HOI is a weaker acid. So the answer for I is HOI. Draw a complete Lewis dot. Electron dot diagram, so it's just HOI, sorry. So I, O, H. H is, there's a bond here, and there's a bond here. O has two lone pairs of electrons, and H, it has only one, it has two electrons in the stable form, and both of them are in the bond. I bonded, it has a full octet. Octet has 8 electrons. So this bond is representing 2, so you need another 2, another 2, and another 2. That's it for the Lewis electron dot. Hypochlorous acid has the formula HOCl. Predict whether HOCl is a stronger acid. To be a stronger acid, it needs to be able to let go of the H plus ion easily. So you have HOCl, and you have a bond here, you have a bond here. So to be able to let go of the acid easily, the electrons has to be sticking more towards here, so the proton, which is this, can just easily drift away. So the closer to this side of the molecule that the electrons are, the stronger the acid is, or the easier it can be let go. The proton can be let go. So since Cl is electronegative, the top right is more electronegative than bottom left or bottom or left. Yeah, so since this is more electronegative, it pulls the electrons more, and H will be able to be let go easily. So that's why it's a stronger acid. Chemical bonding, the O and Cl bond is very electronegative and it's electron dense, which is able to let go of the proton easily. Write the equation for the reaction that occurs between hypoiodous acid and water. It's simple. Hypoiodous acid is HOI, whereas it reacts with water, and then it should form the ion, and the H plus should go to H2O. So double arrow because it's weak, and OI minus, that's the anion from where the H plus left. The H plus is going to leave and go to the water ion and form H3O plus. And that's pretty much it for B. So number C, you have a reaction, they just want the equilibrium constant. So for equilibrium constant, you only include the aqueous, and you include gases if it's only gas, or if it's only aqueous, and you use only aqueous. So OH minus, products over reactant, K is equal to OH minus, here products, HOI, you put it to the power of the coefficients, and since it's only one, you just do it like that, and then OR, products, OR minus. And that is pretty much it for question 3.
Let's start with question 3 of section 14.8. So in question 3, we have given that we have the Ka of two acids, HOI and HOBr, and they're asking us which is weaker, HOI or HOBr, and we have to justify using Ka as our explanation. So I'll give you guys a few seconds and then we'll check. Alright, let's check, and it's very obvious that the weaker acid is HOI. Why is it weaker? Because the Ka value is smaller. That's why the smaller the Ka value, the weaker the acid. So strength goes down. Alright, now I have to draw a complete Lewis electron dot diagram for the acid we just identified. So HOI, HOI. So we have a total of 1 electron for H, 6 for the O, and 7 for the I. We have 14 electrons. The H can only make one bond, so let's just draw one bond. So we got rid of 4 electrons. We have basically 5 lone pairs left. So the O can accept 2. So that's got the octet rule satisfied. And the I can take more than 2 because it's it's a very big electron. It's a very big atom, so it can take more than 8 electrons. In this case, anyways, it's 8. So this is the electron dot diagram. Alright, let's move on to part 3. Hypochlorous acid has the formula HOCl. Predict whether HOCl is stronger or weaker than HOBr. Justify a prediction in terms of chemical bonding. So I'll give you guys a few seconds and then we'll check. Alright, let's check. So HOCl versus HOBr, which is stronger? So we should know that HOCl is stronger as an acid. But let's talk about what makes an acid strong. Well, the strength of an acid is measured in terms of how easily it gets rid of the H, right? Because as we all know, acids are proton donors. So whichever acid can do its role the best, that is a strong acid. So while we should think about this in terms of electrons, if the electrons are in the OH bond, right, then it's harder to take away the H because you need energy to push the electron to the, for example, Cl and O bond and then get rid of the H, right? And if you think about this, Cl and Br, how do we compare them? We compare them in terms of electronegativity. Electronegativity is basically the ease with which an atom pulls electrons towards it. Cl is more electronegative than Br. So the electrons here are more attracted to the Cl, making this bond weak, thus making the ejection of the H plus easier. So that's why HOCl is a stronger one. Br is less electronegative, so it's able to take less percentage of the electrons. So this bond is quite strong, which makes taking the H plus hard. That's why HOCl is the stronger acid. Alright, now we write the reaction, the equation of the reaction that occurs between hypoiodous acid, which is HOI, and water. So let's just write it down. HOI plus water. Now, considering that it's a weak acid, it doesn't dissociate completely, so you have to use a reversible arrow, to give H3O plus, because it's a proton donor, plus OI minus. That's the reaction that occurs. Alright guys, let's move on. Okay, so we have a 1 molar NaOI solution that is prepared by dissolving solid NaOI in distilled water at the, constant temperature. The hydrolysis reaction is given. We have to write the equilibrium constant. So we have to write K equilibrium. Well, we should know that we only put the aqueous and the gaseous atoms in the equation, so we get rid of any liquid. So we get the concentration of HOI multiplied by the concentration of OH minus. Again, we put the power of the coefficient, but in this case all the coefficients are 1 over the concentration of OI minus. Alright, so this is the question 3 down of the previous section. Let's move on to the grid questions. Classify all of them as acidic, basic, or neutral. I'll give you guys a few seconds. You can solve them yourself and then we'll check together. Alright guys, let's check them together. CuCl2. Cu comes from CuOH2 and Cl comes from HCl. CuOH2 is a weak base and HCl is a strong acid, thus making the whole thing acidic salt. A for acidic. K2CO3. So basically what we're looking for is if it's a strong base and a weak acid, it's basic. Weak base and strong acid, it's acidic. Strong base, strong acid, neutral, or weak base, weak acid, neutral. So now we have got our criteria, let's move on. K2CO3. K2 comes from KOH, CO3 comes from H2CO3. KOH is strong, H2CO3 is weak, so it's a basic. FeSO4. Fe is a weak base, SO4 is a strong acid, acidic. MgNO3 Mg is a MgOH2. Okay, when I'm talking about Fe, for example, it's FeOH2, right? MgOH2 is a weak base, HNO3 is strong acid, so it's acidic. Okay, CS3COO2 Ca. CaOH2 is strong base, CS3COOH is weak acid, so it's basic. And NH4 is a weak base, and NO3 is a strong acid, so it's acidic. Now let's talk about section 14.9. Explain how to compare the strength of different acids based on structure. Alright. So basically we have two different types of acids, right? Number 1, oxy acids. And number 2, non-oxy acids. Right? So oxy acids are acids that have an oxygen in them. Anything, HClO4, HOI, anything, blah blah blah. And non-oxy acids are acids that don't come under the oxy acids label, I guess. So first let's talk about oxy acids. What makes an oxy acid strong? Well, if you remember, we were talking about HOCl and HOBr, and we spoke that HOCl is stronger for reasons where we spoke about the electronegativity. So the more electronegative the other atom in the oxy acid, the stronger the acid because it's pulling away the electron, making the OH bond weak. In non-oxy acids, the stronger the bond between the hydrogen and the next one, for example H2SO4, the it's connected to the sulfur. If this is a strong bond, it's a weak acid, because the stronger the bond, the more energy you need to give to actually make it release the hydrogen. So the stronger the bond, the weaker the acid. But the weaker the bond, for example, let's call this a very weak bond, and it's a weak base. It's a strong acid. Sorry, it's a strong acid, because it actually fulfills its role in a better way. It's able to donate the electron, or the proton, the H, better, faster. So that's how we compare the strength. I'll give you guys a few seconds to do basic question 1 for section 14.11, and then we'll check together. Excuse me. Alright. Ethylamine CH3CH2 NH2 is added to a solution of hydrochloric acid. Let's write the balanced equation. So CH3, CH2, and H2. Okay. Well, we should note that whenever we're talking about balanced equations with acid base, if it's a strong acid, we represent only by H plus, not the full formula. If it's weak, we write the full formula. If it's a strong base, we write only OH minus. If it's weak, we write the full thing. So it's obviously, since this is a weak base, we write the full thing. It's a strong acid, we only write H plus. To give CH3, CH2, and H3 plus. That's it. B. Dissolves in water to form a solution, indicate whether it's acidic, basic, or neutral. Well, it's most obviously basic, because it's a base, right? It accepts a proton. So, it's a base, and then, it's a basic solution. Basically, when it goes into water, OH minus are released, because H plus is absorbed. So, OH minus, the presence of OH minus is a base. Basically, that means it is a base. So that's the answer. Alright. Guys, we're not doing the top questions because we're not going to have written in the periodic. So, these are mostly written questions. That's why we're not doing the top questions. Alright guys, let's start with chapter 15. Basic question 1. Calculate the pH of 0.1 molar acetic acid solution in 0.05 molar of sodium acetate, and the Ka is given as 1.8 times 10 to the minus 5. Okay, so let's start. So we should know that acetic acid is CH3COOH, which dissociates partially to give CH3COO minus, which is comes from the sodium acetate, plus H plus. Right, so you have 0.1 molar. This is the ice table, obviously. We have 0.05 already present. We have X of this. We do minus X plus X plus X. So we have 0.1 minus X, 0.05 plus X, and X. Now in such scenarios, we obviously consider X to be negligible. So basically what we have is 0.05 times X over 0.1, because you consider X to be negligible, and this is the equilibrium constant, or the Ka. So 1.8 times 10 to the minus 5. We cross multiply and we get solving for X. Let's see what we get. So 1.8 times 10 to the minus 5 times 0.1 divided by 0.05. We get that X, or the concentration of the H plus, is 3.6 times 10 to the minus 5. To get the pH, let's just continue here. pH is minus log concentration of H plus, so minus log of 3.6 by 10 to the minus 5, giving us an answer of 4.44 to 3 significant figures. So that's how you get. So basically, whenever you have the common ion, we consider the acid dissociation reaction, right? Obviously, if it's a weak acid, if it's a weak acid, it's going to be reversible arrows. If it's strong, the reaction goes to completion. Alright, let's move on to question 1 of section 15.2. Explain how a CH3COOH slash CH3COO minus buffer maintains pH relatively the same upon additions of a few drops of strong acid and strong base. Okay, so how is this a buffer? We should know that it's a weak acid and its conjugate base. So when we add HCl, it's basically adding H plus. So what happens is the CH3COO minus adds that to become CH3COOH, so it becomes the acid. And when we add the OH minus or the NaOH, the CH3COOH adds itself to give the CH3CO minus plus H2O. So what happens is the acid neutralizes the strong base that's added, obviously only a few drops. If we keep adding it, it will change, the pH will change, and the conjugate base takes care of the few drops of the strong acid. So that's what happens, they take care of each other. Alright, so calculate the pH of a buffer solution that's 0.2 molar of NaF and 0.3 molar of HF. Alright, so we should know that we should use the Henderson equation, which is pH equals P of Ka plus log base over acid. Alright, so we'll just get the pKa and then we continue. So I'll give you guys a few seconds and then we'll check together. Alright guys, let's continue with question 2. So this was the Henderson equation. So let's think about how we should solve this question, right? So we should know that, HF is basically dissociating in this to give F minus plus H plus, right? So let's work with the equation. So we have 0.2 molar NaF and 0.3 molar HF. So let's think about it this way. HF is a weak acid and F minus is the conjugate base. So in the Henderson equation is the concentration of base over the concentration of acid. So it's minus log. So Ka is 7.2 times 10 to the minus 4 plus log of the concentration of the base or the conjugate base is NaF, so that's 0.2 over acid 0.3. So when we solve, let's solve this. Minus log 7.2 times minus 4 plus log of 0.2 over 0.3, 2.97, which sounds realistic. So that's the answer. Question 3. Calculate the pH of a buffer solution which is 0.4 molar NaF, 0.6 molar. We won't waste our time with this. We should know that we're multiplying by 2, right? All we're doing is times 2 times 2. So the ratio is the same. And whenever the ratio of base to acid is the same, the pH is the same. 2.97. Okay, a buffer solution is prepared the exact same way. 100 milliliters of water were added. Calculate the new pH. So one thing we should know is that when we add water, we're adding H plus and OH minus. So we add, we're diluting the base and the acid, so we get the exact same pH. 2.97. Question 5 now. Oh, yeah. We have a buffer solution which is prepared of 0.1 molar CH3CONA, which is the conjugate base of CH3COOH, and we have 10 cubic centimeters of 0.2 molar of NaOH, which is added to this actually. So we have to find the new pH. Alright. So again we have to use the exact same Henderson equation. pH is equal to pKa plus log of base over acid. So I'll give you guys a few seconds to check, to solve, and then we'll check together. Alright guys, let's continue with question 5. So first, let's just calculate the number of moles for everything, right? So CH3COONA, we have 100 cubic centimeters of that. So 100 times 0.1, 10 millimoles. 0.2 times 100, 20 millimoles. And for the NaOH, we have 10 times 0.2, 2 millimoles. Now let's write the equation that's happening, right? So CH3 COOH plus OH minus to give CH3 COO minus plus water, right? So what's happening is we have 10 millimoles of CH3COOH, we have 2 millimoles, let's cancel that, and we have 20 millimoles of the CH3CO minus, right? What's the limiting reagent? Obviously the OH minus, so that's completely used up. So we have 8 left here and 18. So now this is the conjugate base. So this is our base and this is our acid. So substituting we get, let's just continue here, pH is equal to minus log, what's the Ka? We have 1.8 times 10 to the minus 5 plus log of 18 over 8. Let's calculate that, shall we? 5.10. So that's the pH of our buffer solution. Alright, question 6 now. A buffer solution of pH 5 is to be prepared using CH3COO and CH3COOH. What should be the molar ratio to achieve this? So this is our base, this is our acid. So what we have is 5 has to equal minus log of the same concentration, which is the same pKa, sorry, plus log B over A, and we have to find B over A in essence. So what B over A actually is let's just write this in for still using the equation 10 to the power of 5 plus log of this. So when we substitute, we should get 10 to the power of 5 plus log. Yes, we get 1.8. So this is our ratio. Because to reverse the log, we have to do 10 to the power because the base is 10. So CH3 COO minus the concentration of that over concentration of CH3COOH should be 1.8 precisely. Alright, so we just take this to the other side and do 10 to the power of that to get the answer. Let's move on to question 7 now, shall we? So we have a solution that is prepared by mixing 70 milliliters of HF and 30 milliliters of NaOH. Calculate the pH. So again, we're basically repeating ourselves here, guys. So it's again the Henderson equation. So let's just calculate the number of moles. 70 by 0.2, 14 millimoles, and 30 by 3 millimoles. So let's just check. HF, because it's a weak base, we represent by everything. OH minus to give F minus plus water. Right? So we have 14,300. Limiting reagent, so that's used up 11,3. This is our acid. This is our conjugate base. Right? So let's work on it. 7. pH is equal to minus log, what's the Ka? 7.25, it's 4 plus log, I believe it was 3 over 11. So let's see what we get. .58, pretty low pH, and that's the answer for number 7. So in such things, all you have to know is are we making a buffer? If yes, we have to use the pH equals the Henderson equation, and then just solve for it. We have to get the number of moles, do some stoichiometry, and then substitute in the equation. So that's it.
Number 8. A solution is mixed by preparing 80 milliliters of 0.3 molar NH4Cl, 20 milliliters 0.2 molar NaOH. So you have NH4 plus, which donates a proton on H plus, and you have OH minus. Together they become water. So NH4 plus OH minus gives NH3 plus H2O. Now we need to find the pH, so let's calculate the concentrations. NH4 concentration or molar. So NH4 plus 0.3 times 80, which is 24, so 24 millimoles. OH minus 20 times 0.2, it's 4 millimole. Then OH minus is limiting, so that cancels out. This becomes 20 millimoles, and this becomes 4 millimoles. H2 was a liquid, so you don't really count that. Now you have these concentrations, then you just apply the formula. pH is equal to minus log, or pKa or B, depending on what this is. Here you have an acid, so you use Ka. My bad, here you have a base, so that's why you use Kb. You choose the one at the end. So yeah, minus log Kb plus log base over acid. And here base is the NH3, which is 4, over acid, which is 20. Log K, A should be given, it's 1.8 times 10 power minus, but you just do 10 power minus 14 over 1.8 times 10 power minus, and then you plug it in and you should get it. We should get 8.55. Next question. Nine. NEF HCl. So F minus plus Cl plus H plus to give HF. Now, is the product a base or an acid? It's HF, so it's an acid. This is the conjugate base. So use Ka. So F minus 60 times 0.2, that is 60 times 0.2, 6 times 2, 12 millimoles. H plus 40 times 0.1, it's 4. So then this goes away, this becomes 4, 12 minus 4 is 8. So base over acid, so 8 over 4. So again, P, Ka, so pH is equal to P, Ka, because it's an acid here, plus log of base, which is the F minus, so 8, over the acid, which is 4. And Ka should be given, which is 7.25 times 10 power minus 4. I don't know why they're not putting it in the question here. And then you should be getting 3.44. Next one, the solution is prepared by mixing 20 milliliters. So you have NH3 plus H plus to give NH4 plus. Now, what's NH4 plus? Is it a base or an acid? Over here. So this is a base, this is an acid. So you use Ka. Next, NH3, 20 of 3 molar, so that should be 60. H plus 80 of 2, so it should be 16. This is nothing. This becomes 16, this gets cancelled out, this becomes 44. So then pH is equal to minus log of Ka. So either they give you Ka from the question and then you use it, or you just do 10 power minus 14, which is Kw, over Kb, plus log of base, which is NH3, so 44, over the acid, which is 16. So you put that in your calculator with the Ka from the given, and you should get 9.69. 15.3, buffered solution. Calculate the pH. You have HF, and then you have Kf minus. Since K is group 1 metal, it will dissolve, so you'll be left with F minus, so plus whatever you have. You don't really need a reaction for this. They straight up give you the base and the acid. So you just do base and the acid, and you have Ka. So pH is equal to minus log of Ka, which is 7.2 times 10 power minus 4 plus log base over acid. This is the base, so 1.9 over acid. This is acid, 1.6. Put in your calculator, you should get 3.21. And that's it for 15.3. 15.4, you have NaOH, HCl, and they're both strong bases, so they dissociate completely. You don't have to worry about Ka or Kb. So Cv equals Cv, 25x is equal to 20 times 0.2. You get x to be 0.16 by calculation, and that's a concentration. Again, you have 0.5 V is equal to 40 times 0.02, and this is 1 over 2, you put that up, you get 80 times 0.02, it becomes 0.2 times 8, you get 1.6. But it's CaOH2, so 2 times that. It dissociates 2 times. So 2 times that, and this becomes 2 times that, is equal to 3.2. Number 2, monoprotic, so you don't multiply by 2 again, is dissolving that. So since it was titrated and needed to reach equivalence point, you know that number of moles of acid, since monoprotic, is equal to number of moles of base. So number of moles of acid is 0.2 over m, which is a molar mass, equals number of moles of acid, which is the number of moles of base, which is NaOH, 0.125, and 20 centimeter cube. So 0.02 times 0.125, and then cross multiply there, you get 0.2 over 0.02 times 0.125, you should get 80. Yeah. Number 3, 25 milliliters of 0.2 molar HA was titrated with 0.2 molar NaOH. pH is 8 at equivalence. What's the Ka of AHA? So here you need 2 ice tables. So ice table, ice, and you first have this and this, which react completely to give HA plus OH minus to give A minus plus H2O. It reacts completely to give A minus. And how much of it? It's this much. So 25 times 0.2, that is 0. Or rather, it's, I'll put it in the calculator. It's 5 basically, yeah. It's 5 millimoles of HA. Now this, A minus at the end when they two react. Now this, what it does is it further reacts with the H2O or the water to give HA plus OH minus. Now this OH minus is what's causing the pH to be 8. And normally you would use Ka to get the pH at the equivalence point. But now it's the opposite. So you have to use this equation and the fact that you had 5 millimoles to get the 8. So how do we do that? Kb, if you just remember the reaction, is equal to products, which is OH minus, into CH3 COOH over CH3 COOH minus. So now what you do is use the, why did I use CH3? It's A minus and HA. Yeah, so A minus, it's given to be from, OH minus from the equivalence points given to be 10 power minus 6. and this is squared because this CH3COO, or sorry, HA, is the same as this, because this dissociates to give this OH minus and HA plus, or HA. So together they are x squared, so 10 to the power minus 6 squared over A, and since you see it's very small, x, you can just use it to be the 5 millimoles from before. So 5 millimoles over 25 milliliters, this titrated with this, because you use concentration, right? So Kb is equal to 10 power minus 6 x squared over, normally you would put the 5 millimoles over 2 times 25 milliliter, because the other 25 is from that, over 0.05, which is 0.1. So normally you would put 0.1 minus x, but you know it's 10 power minus 6, so it's really small, so you just scrap that. So 10 power minus 12 over 0.1, this is Kb, 10 power minus 11, and now Ka is Kw over Kb, which is 10 power minus 14 over 10 power minus 11, which is 10 power minus 3, and that is Ka, and that's number 3. Number 4, the solution 0.1 HCl, 0.1 NaOH, so strong base, strong acid. 40 milliliter sample was solution. Identify solution that was initially added to the beaker. So initially it was at 1, so it was very acidic. And you have HCl, you have NaOH. HCl is very acidic, 0.1. It corresponds to a pH of 1. So answer is HCl. On the titration curve, circle the point equivalence. So equivalence is when you have number of moles of base equals number of moles of acid. So 0.1, the concentration are equal, so the one with same volume, because the concentrations are equal. So the same volume, they're equal, the moles are equal. So 40, it's at this point. At the equivalent points, how many moles of titrant? So I said same mole, they have to exist, so 0.1, 40, and then times 10 power minus 3, because it's milliliter and you need it in liter. The same titration is to be performed again, this time using an indicator. Okay, to find the indicator, you need to find the pH range at the equivalence point. So equivalence are the same number of moles is between there. So between 3 and 10 to 11. So the one that corresponds is this one, because it's in the middle of the range. So bromose, cresol, purple. What's the difference between equivalence point? Equivalence point is when the number of moles are equal. End point is when the color actually starts to show. That's when you just completely stop. Equivalence point, you might still be dropping 1 or 2, even though it will be excess. On the grid below, sketch the titration. It's the exact same, but just flipped. So if you put a line in the middle at the equivalence point, it's just reflected like that, and then like down there, and then down like that. So if it was on this grid, it would be something like that, and down, not horizontal, just like that. That's horizontal still. This one's more vertical like that, something like that. You have a pencil, you'll be able to properly arrange it. Number 5. A pure 15.5 gram sample of the weak base methylamine. So weak base, so dissociation is CH3 NH2 to give CH3 NH3, and this is H3O plus and H2O plus, and H2O, sorry, plus that, and this is Kb, because it's dissociating. Right. So calculate the molar concentration. It's C is equal to N over V. N is mass over molar mass, so 15.5 over 31, which is 0.5. So 0.5 over 1000 milliliters converted to liters, which is 1. So 0.5 the answer. Now part B, the K equilibrium constant. So aqueous products or gases over aqueous or gaseous reactants. So CH3NH3 plus times OH minus over CH3 and H2 concentration. That's the equilibrium of law which is present in the solution at the higher concentration. Okay, so we know it's a weak base, so the dissociation is less. So this should be present in more because it won't dissociate as much. Otherwise, it would be called a medium base or a slightly medium base. A different solution is made by mixing 500 milliliters of that and 500 milliliters of HCl. Assume volumes are additive. pH of the solution is found to be 10.52. Calculate concentration of OH minus. You have pH, so it's simply 10 power minus POH, which is 14, minus pH, which is 10.52. Put it in the calculator, and you should get 3.31 times 10 power minus 4. Write the net ionic is mixed with HCl, so CH3 and H2, and since it's weak, it doesn't dissociate, it doesn't react immediately, so that's why it has time to react with water and form H3O to give CH3 NH3 plus H2O as the dissociation reaction. Now we're going to use that for the next question. Calculate the molar concentration of CH3 that is formed. So you have 500 times 0.2, which is 50 millimoles, minus 500 or with H plus, which is dissociating completely. And I said weak base, I was wrong. It was weak base here because it reacts with that. It's not a weak acid, it's a weak base, but this one is a strong acid. So with 5 millimoles or something similar. You don't need to do it now, you'll find out later on. As you can see, this one is more than this because same volume but greater concentration. So use the HCl. So HCl, that's the limiting. It reacts completely to form this one. So to get the NH3 plus, you use that. So 500, which is 0.5, times 0.1 is equal to 0.05. And that's the answer for part 3. Next one, value of Kb. Kb is, you simply use, it's the dissociation of this. So CH3 and H2 plus H2O to give CH3 and H2 NH3 sorry plus OH minus. This is Kb. It's this dissociating into its ions, or when it gets the H plus. So calculate the value. It will be Kb is equal to OH minus, OH minus, this one here, into, you're using the products, CH3 NH3 plus over this one here, so CH3 NH2. Let me simplify that. So we do that from, we got from before that 0.05 of CH3 NH3 plus was produced. So that means from this 0.05 was used up. So into 0.5, yes, 0.5 times 0.25 minus 0.05 over, well, you don't need to put over because it's 1. So 500 plus 500 ml is 1000 ml, which is 1 liter. So you don't have to worry about it because 1 doesn't really affect the situation. And then OH minus, where do you get it from? You get it from the original. You found it to be 10.52, and you found the original, which was 3.31 times 10 power minus 4 from part I. The pH is that. Now put this in your calculator, you should get 2.21 times 10 power minus 4. And that's it for 5. Now the grid. 50 centimeter cubed and NO3, pH of the solution, no base is added, easy. You have this concentration already, so minus log 0.5, and the answer is 0.3. When you put in the calculator, you get that. Next one, minus log, this is for any P. Now concentration of H, you have this, but you added 10 centimeter cubed of bases. So now you do CV equals CV to find the new V, or you're not diluting it, you're using it up, but you do it in that form. So over 60, and then moles are here. Concentration is moles over volume, so 50 plus 10, 60. Now to find the moles, it's 50 times 0.5 minus 10 times 0.5. You can use 50 and 10 because they cancel out over here. So if you had times 10 power minus 3, it would have cancelled out. And you put in the calculator and you get 0.48. See? 150 centimeter cubed. Look at this. They're the same. So you can just directly tell that it's 7. Now 60 centimeter cubed. So you have 50 plus the 10. So 50 cancelled out the acidic. Now this 10 is contributing to the base. So you now have, it's like saying now you have 10 centimeter cubed of 0.5 NaOH. But you have it in 50 plus 60. Or 50 plus 60, because now it's diluted like that. So it's like a CV equals CV question. Put it in the calculator to get the number, to get the moles, and minus log. Now if you do this, you get the POH, so you just do 14. 14 minus, you get the pH. Draw titration curve for the change of pH versus volume of base added. In your curve, the following points have to be clearly indicated, the pH before the titration start. Okay, so you have the points from before. You draw a curve, you label it pH, you label volume of NaOH added, and you just take the points from before. So 0 is 0.3, so somewhere here, and then it slowly goes up. Then at the pH point it slopes upwards, and then it shifts off to the basic. That's the pH curve. And that's it for number 1. Number 2, 50 centimeter cubed of 0.1 molar CH3COOH. Find the pH of the solution when no base has been added yet. So no base has been added, and this means that this basically means that you have this molar only with dissociating this much by Ka. So CH3 plus H2O to give the COO minus. So a quick way to do it is just square root the OH minus, or H plus, square root of 1.8 times 10 power minus 5 times 0.1. This is the H plus. Then you do minus log of that, and you get 2.87. And let me just pull it up here. 2.87. Find the pH of the solution when 10 milliliters of base has been added. So now you're adding a base. So now the equation becomes plus OH minus to give COO minus. I'm just going to put the short form, plus H2O. So that one is there, inclusive. So it was 0.1 times 50, which is 5 millimoles, and OH is 10 times 0.1, which is 1 millimole, and then this becomes 1. So pH of solution is pH is equal to pKa, which is minus log of 1.8 times 10 power minus 5. Although, should we use PB, KB? No, because you have the acid initially. So pKa plus log base, which is 1 over 5. 4, because subtracting 1, because you got used 1. Put that in your calculator, and you should end up with 4.14. Next one, find the pH of the solution. 25 centimeter bases are added. 25 centimeters, 50 centimeter here, so that's half of it, and since they're the same concentration, you know you have reached the half equivalence point. At the half equivalence point, the H plus is equal to the Ka, is equal to 1.8 times 10 power minus 5, so that's the answer. So H plus is 1.8 times 10 power minus 5. That's for pH, so you do pKa, and if you do that, it's minus log of 1.8 times 10 power minus 5, you get 4.74. Next one, D. Find the pH of solution when 50 centimeter cubed base are added. 50 centimeters, which means all of this became COO minus, and then COO minus, and then it goes back into being OH minus plus H2O plus COOH. So you're left with 5 millimoles, or you have 5 millimoles of COO, and then since it's a minus here, you use KB. So 5 millimoles divided by, to get the molar, and because for K you're working with molar, and then 50/50 divided by 0.1, which is 50 centimeters plus 50 centimeter, 100 centimeter cube, which is 0.1 decimeter cubed, or 0.1 liter. So that means you have KB, it's equal to OH minus into COOH, CH3COOH, into COO minus, COO minus. Now COO minus, you got it at 0.05. But 5 OH minus, that's what you need to find. That's X. And then COOH, you use it from the previous one. Part D, find the pH of the solution when 50 centimeter cube base added. So 50 centimeter cube, 50 centimeter, 0.1, 0.1. So all of it reacts to form COO minus. But now, some of the COO minus reacts to release OH minus, and then using this OH minus, you calculate the pH. So how do you know which? You use a KB equation, which is equal to CH3COOH into OH minus over CH3COO minus concentration. Now, you don't have this, so they're 0 at this time. So you can just represent them as X and X both, like ice table. If you do it, you'll get it. And then this, you need to calculate CH3COO. well, this all of this reacts, so it's simply 0.50 times 0.1, which is 5 millimoles, so 0.05, over 50 plus 50, 100, which is 0.1. So now this is 0.05. So x squared over 0.05 minus x equals kb, where it's equal to kw over ka. That's messy, but yeah. So this is equal to 10 power minus 14 over ka, so 1.8 times 10 power minus 5. Then you put in your calculator, or for things not to get messy, you can take this as 0, because it's negligible compared to 0.05, and then x becomes square root of 0.05 times 10 power minus 14 over 1.8 times 10 power minus 5. So that's 5.27 times 10 power minus 6 OH minus. So you just do, so keep that number in mind or in your calculator. So you do TH is equal to 14 minus POH, and POH is minus log of the answer you just got, which is 5.27 times 10 power minus 6. So put that in your calculator, you get 8.72, and that's what the answer is. Now find the pH of solution when you add extra base. When you add extra base, you reacted all of this, but now you're also having 10 centimeter cubed of the extra OH minus. So 10 centimeter cubed of 0.1 molar, you get it to be 1 millimole in 110, which is 50 plus 60 base times 10 power minus 3. And then millimole, 10 power minus 3, they cancel, so now you're left with 1 over 110. And that is the concentration of OH minus. And then to get the pH, you do 14 plus or minus log, so plus log of 1 over 110. And indeed, you get 11.95 or 11.96. Draw a titration curve. This is a weak acid with a strong base. So the titration curve is something like this. So the key features to note are the little concave part here, and then the straight part here. It's supposed to be almost straight. This in the middle, and then here it just approaches the certain value of pH, which is probably 14, but it never reaches it because you have to add infinite OH minus, and that is 15.4. Now 15.5, which is a bit easier because it's a bit more handly, you can handle better. Find after addition 12.5 NaOH. The pH of the resultant solution is 4.74. So we're calculating each of the following. Since the pH is 4.74, you just equal it to, this is, if you notice, 12.5, 25, it's a half equivalence point at this point. So pH is 4.74, so H plus is 10 power minus 4.74. Put in your calculator. Minus 4.74. You get 1.8 times 10 power minus 5. That's H plus. And then to get OH minus, you just do 10 power minus 14 over that. And you should get 5.56 times 10 power minus 10. The number of moles of NaOH added, you just do that. CV, N equals CV, and then times 10 power minus 3. So if we were to solve it, it would be 1.25 millimoles. Number of moles of CH3CO minus in the solution, here, 20 millimeters of that. Well, that's OH. So here you have this. So let's do ice table. But this is not plus OH now, and H2O is formed. So ice table here, 25. So 2.5 millimoles. Here you have 1.25, and here you have CH3CO, nothing on this one here. You have nothing. But now this OH minus reacts, so you have nothing there. You have 1.25 there, and you have 2.5. It becomes 1.25. So number of moles of CH3CO minus 1.25 from here, CHOOH 1.25 from here. So since you see they're equal, this is a half equivalence point. On the base, on this base and this acid are equal, that's a half equivalence point. State whether the solution is acidic, basic, or neutral. The correct explanation is you have a solution of CH3CO minus, the ion dissociates in water to release OH minus, that's why it's basic. So CO minus, you have it in the flask, and then it releases OH minus when it comes into contact with water, because you need to form CH3COOH. In a different experiment, 0.118 grams was mixed. Calculate the mass in grams. So 0.118 is a mixture of these two, and in the equivalence point, base equals acid. So acid is 0.1, 10 milliliters. So base is 0.1 times 10 times 10 power minus 3, that's the number of moles of base, is equal to number of moles of acid. So that is the number of moles of acid. So to get mass of that is equal to number of moles of base, aka acid, times molar mass, which is CH3COO, it's 60. So now you end up with 0.1 times 10 power minus 3 times 10, so times 2 times 60, 0.06. So 0.06 over 0.118 to calculate the mass percent, and divided by 0.118, you get 5%, or 50.8%, sorry. And let's see, calculate the pH at the equivalence point of 25 milliliter 0.1. It's simple, it's like the first one. You calculate CH3COO minus, and then square root of that times Kb. Because of dissociation, this is releasing OH minus, then you use the OH minus to calculate pH. Now Kb is 10 power minus 14 over 1.8 times 10 power minus 5. CH3CO, you use it from this. It reacts perfectly, or it reacts properly, so you get all of it. So it's 0.1 times 25 times 10 power minus 3. You get the OH, this concentration of OH, that's equal to 1.17 times 10 power minus 6. To calculate pH, it's equal to P, K, not now, that's the wrong equation. It's equal to 14 minus POH, and this is minus log of OH minus concentration. And you end up with 8.72. Yes. And then E, 8.72. Which one is the closest? It's simply this 9.2 over here. And that is pretty much it for 15.5.